quite a few here now, George, so I think we will get going. Welcome to Santa, Star Wars and Sums. Really pleased that you could join us this evening for a GCU Christmas lecture. I am Susan and I'm the university's Community and Public Engagement Coordinator, and I'm here this evening to support George. So if you have any comments or questions during his talk, then you can put them in the chat and I'll be keeping an eye on that and I can ask him them for you at the end. If, however, you would prefer to wait and put your audio on at the end of the talk and ask any questions that way, you're very welcome to do so. As I said, I'll also be keeping an eye on the wait room. So if you have to leave for any reason or your Wi-Fi cuts out or something and you want to rejoin, then that's fine. I'll let you back into the room. You can also message me privately as well. If there's anything I can help with, then please do so. And otherwise, I think that is everything. I hope that you enjoy this evening. We're planning to finish for 8 o'clock. We are recording the session, but it's only George's talk that I'm recording. I won't share any content with audience members. And I hope you enjoy it. I'm going to hand over to George, who I hope is going to convince me that Santa exists.
Oh, I am, hopefully. Hello, everyone. I'm George. A couple of things about me, so you can get an idea of why we're doing what we're doing today. I lecture things that have to do with energy, but one of the things I talk also about is quantitative research methods, in which we use math to prove and disprove things. Basically, we use it as a tool of research. And I have fun with it. I like it a lot. I think it is very interesting. I think it will give us a very interesting, a very nice perspective to things that we're doing. And one of the reasons I wanted to do this today is because many people see maths and they're very scared of, they're afraid and so on. And to be fair, maths has a reputation of being a little bit dry. So today we're going to be analyzing things like Santa Claus and Star Wars to see that, you know what, maths can potentially be fun. So let me start sharing my screen with you and let's get this show on the road. I did tweak the title a little bit, I'm really sorry, but yes, we do have a little bit of physics in there as well, but bear with me, I'm pretty sure everything will be fairly easy to understand. Now, I don't know about you, but I grew up knowing that there was no Santa. So I never had to actually prove to myself that there wasn't, but proving that there isn't has its own charm. As with any mathematical proof, as with any basic thought in life, we have to come up with certain assumptions. So I will be giving you a list of assumptions, follow along with me and let's see what we can discover. So let's get this show on the road. I will be using rough figures, so whenever I see extremely strange numbers, I will be rounding things to make things easier to digest. We have around 2 billion children in the world. And I'm talking about children because children is the main focus of Santa. I know that Santa likes to visit older people as well, but most of the times it is addressed towards Santa. If you look at official statistics, you will see that 33.51% of the world follows a Christian religion. It might be Catholic, Protestant, Orthodox, and so on, but they follow a Christian dogma. And I'm mentioning this because Santa Claus and all of the other incantations that it has, Saint Nicholas and so on, are a Christian tradition. Therefore, from that we can presume that we have a certain percentage of those children being eligible for Santa. If you look at the numbers, you see that we're talking about 6,700 million. We cannot have any more because we might have very good kids being Buddhist and Hindus, but unfortunately Santa is a little bit discriminatory when it comes to this. The average children per household, again, if you look at statistical data, is 2.1, which means that on average, we can presume that we have 320 million households that are eligible to receive a visitation from Santa. Okay, let's carry on. This data comes from the World Bank. You can go in and check it out. It's not like I'm making these numbers up. Let's continue our assumptions. Now, I know that Santa only visits good kids. And to play it fair, we can assume that, okay, there is only one good child per household. There could have been two, but let's assume it is only one. As you will see later on, the only thing that would change would be the numbers after all. That leaves us with 320 million children that are eligible to receive a gift. Now, we start to make some assumptions to make our analysis better. The first thing we can say is that we can assume that we have an even distribution of houses around the globe. In reality, that's not the case. You have the globe here. Hopefully all of you know that the Earth is a globe and not flat, by the way. So we have the globe and we have some houses here, typically gathered mostly around cities. In order to make our analysis better, though, we can disregard this and say, let's assume that all houses are evenly distributed everywhere. That means that if we know the landmass of the Earth, which is this huge number in there, we can make a very simple division and we can see that for each house we have, we can assign an area around it equal to 0.47 square kilometers. So basically, we have a square. In the middle of each of these squares, you have a house. You have a square here, a square here, a square here, and so on. The square is made up from a length and a width of 0.68. That is because 0.68 times 0.68 gives you 0.47 square kilometers. As such, we can presume that the distance between all of the households is 0.68 as well. Now, in reality, that's not the case because you have a house here, and then you have a house next to it, and then you might have a house on top. So the distance between this house and the house on top might be a little bit more, if you remember from the Pythagorean theorem. But again, for the sake of simplicity, let's say 0.68. Now we have to think about how fast this thing can happen. If you think about it, Santa only has 24 hours to work. Christmas Day. Now in reality, because the Earth is rotating and the sun and Santa can go around that way, he can cheat his way around and gain some extra hours. Because that would make things a little bit more complex, let's stay with the assumption it is 24 hours. Which means Santa has to visit 13 million households per hour or 220,000 households per second. Otherwise, Santa doesn't have enough time to cover everything for Christmas Day. Okay? Which means every visitation lasts 0.0045 milliseconds, or if you would rather have it in seconds, 0.0000045 seconds. Which means that the average speed that Santa Claus should have in order to cover that distance in 24 hours should be a whopping 150,000 kilometers per second, which happens to be 50% of the speed of light. And I know it sounds massive, but the good thing is that physics doesn't put a hard stop in this. The maximum velocity we can have in the world is the speed of light in a vacuum, which is 300,000 kilometers per second. Therefore, there is no physical barrier. So we can, in theory, say, okay, let's assume Santa had a way to travel that fast. Therefore, he could do that. Okay, fine, I'll play along. Let's talk about the weight though. Every child gets a present. Now, some kids might get very heavy presents, some of them might get very small ones, but let's say that on average, every kid gets one present that weighs 1 kilo. Santa has nine reindeer: Dasher, Dancer, Prancer, Vixen, Comet, Cupid, Dunder, Blixen, and Rudolph, although some of those have other names. For example, Dunder is also known as Donner, but that's a different story. And typically, every reindeer weighs around 170 kilos when it has reached adulthood. Again, on average, you get bigger species and smaller species, but that's a nice average. Santa is a bit on the heavy side. I'm putting down 120 kilos, but he could be more. But in the grand scheme of things, compared to the weight of the presents, the weight of Santa doesn't play a big role. That being said, though, we have other things to consider. The weight of the sleigh is 100 kilos. If you make a sleigh out of pine wood, for the size to fit one person, it would roughly be something like that. I am not including the size of the presents here, although I should, but I'm giving Santa benefit of the doubt. So if you were to add all of that weight together, you would find that the total weight would be 320 million kilos, which is fairly heavy. So let's talk about physics for a wee bit. The kinetic energy of any moving object in the world is given by half multiplied by its mass multiplied by its velocity squared. Everything that moves carries with it some energy, otherwise it won't be able to move. Now, if you were to use meters per second for the velocity, and if you were to use kilos for the mass, the result would be in joules. The joule is a very small energy unit, and as such I'm using the watt hour, which is a very common unit. We use it a lot when we pay for electricity. So if you were to punch the numbers in, you would find that the kinetic energy of Santa, all the reindeer, the sleigh, and the presents would be a whooping that number then. I think that's 1 quintillion terawatt hours, which is a lot. But again, that alone doesn't say much, because in theory we would have that energy. We don't know that. Okay, the world energy consumption back in 2015 was 168,000 terawatt hours. It kind of increases on a yearly basis, but only by a tiny amount. So that number, or that that number, let's say, kind of stands. Which means Santa, for a single night, requires 600,000 times more energy than what the world uses in a whole year. If we had Christmas every night, like some songs suggest, Santa would need 219 million times more energy than what we would consume in the same period, which is massive. But that amount of energy might exist. We don't know how much coal we have, we don't know how much oil we have. Perhaps we could burn everything to power Santa's sleigh. Now, a big disclaimer is that we do know how much of those we have, but let's assume that, okay, there isn't a physical limit. If you can find that amount of energy, we could, in theory, make Santa move like that, which is fine. I think it's time to start investing a little bit in renewable energy more, but let's carry on. So, where does this bring us? We have that amount of time, and for that amount of time, Santa has to go down a chimney, leave the presents, eat the cookies, go up, and take off to continue and continue and continue. Traditionally, we leave things for Santa to eat. In Greece, for example, we leave something called kourabies, which is like a shortbread with powdered sugar. Here, we typically leave shortbread and whiskey and so on. I love chocolate digestives, so let's assume that we leave chocolate digestives to Santa. One of those has 83 calories, which means Santa will have consumed 26 billion calories. He will go down all of these houses and eat the cookies. He's not working for free after all. I require around 2,900 calories daily. Because of my lifestyle, I walk a lot, I go to the gym, I tend to have a higher caloric intake than somebody else. Typically, you would find that most males would be around 2,500, something like that. Which means Santa will consume in a single night what I need for 9 million days or 25,000 years. Or if you were to flip it completely, you would say that in a single day, Santa will consume the same amount of calories that people in Scotland and Uruguay eat together combined. So I don't think it is very economical to feed Santa, but it is what it is. Plus, because of all these calories, he will put on some weight. 1 kilo of fat contains 9,000 calories, which means, based on the calories he will have consumed, Santa will put on around 3 billion kilos of fat, which is a bit excessive. He will also put 500 grams of glycogen, which is more or less what we can store. If you're way bigger and more muscular, potentially you could store some more, but this is what it is. As you can see, fat grossly outweighs the muscle glycogen. The good thing is that the sleigh constantly gets a little bit lighter. So at least we're gaining something on that aspect. Of course, we're not done because that amount of food exists. We can produce it. We can make as many digestive biscuits. It will be expensive and so on, but we have the means to do that. So we haven't actually disproven anything yet. Here's a problem though. The amount of energy the amount of energy that the sleigh has to come from its transport, has to come from its engine. The sleigh doesn't have any engine. It is being pulled by the reindeer, which means the amount of energy that is present in the sleigh has to come from the reindeer themselves. Since we have 9 reindeer, each reindeer should be able to provide that many terawatt hours. You take the previous value and you simply divide it by 9. Now, reindeer eat leafy greens, mushrooms, carrots, and so on. They're vegans, as you can imagine. So I think it is a fair presumption to say that since they fly, they are magic. Therefore, the most ideal food for what they have would be probably magic mushrooms. 1 kilo of mushrooms contains 220 calories, or if you were to have it in watt hours, 0.256 kilowatt hours. Depending on the type of mushrooms, you might have a higher calorie count or a lower calorie count, but 220 is a good average. I think I was using portobello mushrooms for this, but I don't remember, to be honest. Since they are magic, we can assume that they have a magically effective metabolism. Therefore, they are converting 100% of what they eat to kinetic energy. In reality, that number is way, way lower. We consume calories to be alive, and out of these calories, a large amount is spent to retain homeostasis in our body, basically our body's ability to retain the same. We repair our tissues, we grow, and we can produce movement as well. This is why we're able to move around. Typically, for the average human being, that number is around 25%. So basically, our metabolic efficiency from food to movement is 25%. And it is more or less the same for most large mammals. But again, they are magic, so let's say 100%. That means that each reindeer needs to consume 436 billion tons of mushrooms. That's a lot. And there is a problem here. There was an amazing study that came out a couple of years back talking about the biomass distribution on Earth. These 2 researchers counted how much biomass we have on the planet. If you don't know that, biomass is any kind of mass that has biological origins. So biomass includes plants, plant life, fungi, and animals. Everything that is alive is counted in there. And they found that the total mass of life on Earth weighs 550 million tons. And here we reach a very big problem. Because the total live mass of Earth, the amount of mass that is able to be consumed, is 1/1,000,000th of what a single reindeer requires. So now we reach a point where it is physically impossible for this thing to happen. Simply put, there isn't enough food to feed the reindeer so the reindeer can provide that amount of energy to make the sleigh move that fast that it will allow Santa to deliver all the presents. Therefore, either Santa is lying and not everybody is getting presents, or Santa doesn't exist. And I am willing to say that Santa doesn't exist based on those things. Of course, I'm not done. We can consider the excrement volume of reindeer. Reindeer would somehow have to get rid of the food they ate by producing waste, poop. How much of that would they produce? Is there enough space on Earth to actually have all of that, or does it have to magically go away? We have to think about the grazing land for the reindeer themselves. They eat the mushrooms and the carrots and the greens and so on, but do we have enough land mass to do this? What about the aerodynamic resistance of the reindeer themselves? The sleigh isn't moving in vacuum, it is moving through air. And air is made up from different elements. It is made from argon, nitrogen, oxygen, carbon dioxide, and so on. And these have some amount of mass. So while the sleigh is moving through them, friction is happening, therefore the sleigh would heat up. And the faster you move, the more of that happens. Reindeer will eat the mushrooms, and thus their stomach will start getting bigger and bigger and bigger. Since they have to consume that amount of mushrooms, how big will their stomachs have to be? Or how elastic should their stomachs have to be? That causes a very big problem. What about the extreme acceleration and deceleration of the sleigh? If you only have 0.0045 milliseconds to reach light speed, or not only to reach light speed, to reach light speed, stop, go down, go up and take off again, that would cause extreme stress on the neck. Probably concussions. If you consider the time zones, then you can think about perhaps possibly Santa having more time. And if you know some physics, you know that when you move at extremely high speeds, like the one we discussed before, you start to experience relativistic phenomena, which means distances change and mass changes and so on. Now, the funny thing about this analysis is the fact that you can tweak it to see all of those things for yourselves. You have seen how many mushrooms they need, let's see how much land they have. Or let's see how much poop they would make and so on. So you would find many other things that prove that Santa probably doesn't exist. So what's the point of doing this? Well, the point of doing this is that the math I'm using here is math that we all know. We learned these when we're what, 9, 10, 11 years old? So why are we doing these in other aspects of our life, such as Star Wars, for example? Let's talk about Star Wars. I'm talking about Star Wars because Star Wars is a Christmas tradition. All main Star Wars movies, with the exception of Solo, which isn't the main Star Wars movie, it is a standalone, came out in Christmas period. It has always been a Christmas affair. So in my mind, because I love Star Wars to death, it is tied very well. So let's start with the basics. If Star Wars was real, that means they would have Jedi, and when you think about Jedi, the most iconic thing you can think of is a lightsaber. So let's see how much lightsabers actually cost. Are they realistic? Could they actually exist? Now, the closest thing we have to a lightsaber is something we call a plasma cutter. It is used to cut metal. Lightsabers, if you look at the lore, are made from plasma. So we can safely assume that a lightsaber is a glorified plasma cutter. Okay. Steel melts at 1370 degrees. The specific heat capacity of steel is 502 joules per kilokelvin. The heat capacity of something shows the ability of any material to absorb energy. So basically this shows how much energy steel can absorb before eventually melting and becoming a liquid, potentially. So we don't know if steel exists in Star Wars, but if you look at the lore, you will see that there is a material called durasteel that has exactly the same characteristics, and this is what spaceships are made of. You can find this data on Wikipedia, which is an amazing website. I highly advise everyone to look at it. We also know that the temperature in spaceships is fairly okay. We have seen people walking around in fairly light clothes, so it is a fair assumption that the temperature is what, 20, 21 degrees? Something like that. Let's say 20. The best depiction of how powerful a lightsaber is was shown in The Phantom Menace. Indeed, in that we had Qui-Gon Jinn taking a lightsaber and plunging it right through a steel door. And the steel door, the durasteel door, was so thick that the lightsaber barely made it at the other end. Now, if you think about it logically, if you're pushing something through something that is solid, and you know that your lightsaber, is extremely hot and has the ability to melt other things, what you're actually doing is you're melting the steel as you're going through. Hence, you were able to push through it. A lightsaber isn't a solid object. Therefore, what happened is that the lightsaber opened a cylinder of molten durasteel across the durasteel door, and therefore it was able to punch through. And we have seen that this happened extremely fast. Now, I didn't time it, but that happened in around a second or so. Liam Neeson, who depicted Qui-Gon Jinn, simply did this very quickly. So that builds other assumptions. Liam Neeson is a fairly tall guy. I think he's like 1.90 meters, something like that. So if you look at his proportions, and if you look at the lightsaber, you can see that the length of the lightsaber is around 1.2 meters long. And the thickness is around 3 centimeters in diameter. In fact, you can find data like that, again, in Wikipedia, which is one of the best things about Star Wars lore. If we assume the blaster was indeed made from durasteel, and we know that durasteel has a density of 8,000 kilos per cubic meter, and we know that the lightsaber went through the door at 1 second, we can find out the power needed to do that. There is a very nice formula in physics that shows how much power you need to require in order to raise the temperature of something to something else. So basically you had solid steel at 20, and you know that steel became a liquid, which means your steel had to reach a temperature of 1,300 and something Celsius. Which means that the temperature difference of the steel before and after is around 1,300 degrees. So by punching the numbers in the formula there, what we can find is that the lightsaber was able to punch through 0.84 liters of steel, which is equal to 6.8 kilos of steel, because we know the density of steel. And if you punch the numbers in, you see that the power output of the lightsaber itself is 4.6 megawatts, which is good news because that's the size of a medium to large wind turbine. Or if you want to have something more relatable, that is the same power output that 1 million fairly slow phone chargers can give you. And the good thing about this is that this amount of energy, this amount of power, is fairly small. It is very easy to have. So lightsabers might be a thing. If you look at the Star Wars universe, the average duel lasts around 1 minute. So for 1 minute, a power output of 4.6 megawatts gives you an energy usage of 77 kilowatt hours. The average UK electricity price is 14.5p per kilowatt hour. So every lightsaber duel that lasts a minute costs 11 pounds. Which is amazing, because if you ask me, if somebody were to say, take this lightsaber and swinging it around for a minute, I would gladly pay 11 pounds and even more. I would love to have a lightsaber. So up until now, lightsabers are a thing. But the iPhone X has one of the most advanced batteries that we currently have. It has a capacity of 10 watt hours and it has a weight of 120 grams. In order to reach the capacity we require for the lightsaber to run for 1 minute, we will be needing 7,700 batteries. And here is where we run across problems. The amount of batteries that we would need for the lightsaber to be on for 1 minute would be a whopping 924 kilos. And we have seen that most Jedi who are human, are typically normal humans. Even if you look at Wikipedia, it's not like they're super strong humans. Therefore, it is completely impossible for them to be able to wield a lightsaber. And now you might say they're using the Force to help them. And the answer is yes, but everyone can actually wield a lightsaber, even if they're not Force sensitive. Which means it is impossible to assume that lightsabers can exist, simply because they would be extremely heavy. Not good news. But of course, I'm not done. Let's talk about the Death Star, another huge iconic thing from Star Wars. The very first time we saw the power of the Death Star was when it blew up Alderaan, the place where Leia grew up, because she was not the stepdaughter, she was taken in by the Organa family, who ruled over Alderaan. Earth has a mass of that number. If you don't know, 10 to the power of 24 simply means 24 zeros after the number we have. So Alderan has more or less the same mass. Tungsten is an element that has the highest melting point of all of the elements in the world. It has a melting point of 3,500 degrees. But in theory, we can make elements that have a melting point of up to 4,127. Simply put, that means that everything we know of in Earth would be liquid if the temperature was above 4,000 degrees. Okay, so let's play some extremes. Let's assume that Alderan is a solid ball and it is made from this ultra-resilient material when it comes to melting. We also saw that Alderan actually blew up in a single second. So let's try to calculate how much energy we would require for Alderan to melt and potentially blow up, because we saw that Alderan was able to blow up. If you punch the numbers in, again with the previous formula, you would find that Alderan would require a power input of 3 times 10 to the power of 21 megawatts. That doesn't say much, unless you actually see how this is related to other things we know of. Our sun emits 3.8 times 10 to the power of 20, which means that our sun is 1/10 as powerful as we actually need, or if we were to flip it, we would need the power output of 10 suns to be able to focus all of their output in a single beam in order to be able to melt Alderan. But we have seen that wasn't the case with the Death Star. The Death Star was able to simply move along and fire a laser. But the problem is that melting isn't enough, because Alderan wasn't melted. Alderan was exploded, which means you need to find a way to overcome the gravity field of the planet. Otherwise, it would melt but still stay where it is. So, let's see what is happening now. The gravitational energy that is holding the Earth together is 2.5 times 10 to the power of 32 joules. This is a constant, you can find it if you look it up. This is how much energy basically the Earth needs in order to stay where it is. If you use the power output from the sun that we had before, and keeping in mind that power is nothing more than how fast we use up energy, we find that our sun alone would take 600,000 years in order to produce enough energy to destroy Alderan. 600,000 years, but we saw that this thing happened in a second. So, how much power would we actually need to do that? If you wanted to do it in a second, you would require 2 times 10 to the power of 13 suns. Or, if you'd rather see a big number, you would require 2 followed by 13 zeros. Because of that, I tend to think that the Death Star doesn't exist. Now, to be fair, in the 7th movie of the series, the one that came out in 2017 called The Force Awakens, we saw Death Star Plus called Starkiller Base. And we saw that this base was actually absorbing energy from a star and redirecting it. That's a good idea, but you need a little bit more than one in order to do that. And because of that, I'm really sorry to say, but I don't think the Death Star could actually exist as well. But, okay, this is just a fun analysis and so on, but what's the point? Well, the point is that you can use analysis like this and get serious points across. So now I'm toning down the humor, if you can call that humor, and I'm upping reality. We all know that in the latest American elections, the US American elections, Joe Biden won against Donald Trump. If you look at the results for the last 8 elections, on the left-hand side, I have the loser of the election. On the right, I have the winner of the election. In between them, I have the amount of votes they got in million. So Trump had 74.2 million and Biden had 81. Then I saw the population of the US and I saw the percentage that the loser and the winner got. And I also saw the difference they had, both in terms of percentage, but also in terms of votes. Now, due to the strange US election system, there were 2 elections, the one where we had Trump against Hillary Clinton and the one we had Bush against Gore, where the people who got the win were the people who got less votes. This is why you see these minuses. Now, why am I showing this? Let's try to analyze them in a biased, in a polarized way. Let's say that you wanted a certain category of people to feel like Trump won. Basically, if you were to take the hard right of the US politics and you were to say, these are typical Trump supporters and they're a bit let down, so let's give them something that will empower them. I should open up a parenthesis here and say that this by no means is a run against Trump. I'm just simply talking about Trump because he was the loser of the election. So let's see what we can come up with from the set we have. The statements I'm going to give you are absolutely true, all of them. Trump had the largest number of votes in history up until the elections. It is true. Trump was by far the most successful Republican ever. Again true. He had the largest vote percentage in history up until the elections. Again true. He had 27 million more votes than the biggest winner in history, who was Bill Clinton. Again true. He had 20% more votes than the most successful Republican before him. And if you were to go the anti-Biden route in order to back up this, Biden was the second worst Democrat winner in history. So why do I say this? All of this is true, completely true. It only has to do with how you look at the numbers. And unless you understand how people come up with these numbers, it is very easy for you to get polarized. By reading statements like this, you're saying, why didn't Trump win? Somebody is messing with the election. And that can cause things from people strengthening their political beliefs to actually rioting. And that simply stems from the fact that we don't read the numbers very well. We don't necessarily understand what these numbers mean. And it's a real shame. We can use numbers to convey meanings and make them different. Without lying, without changing anything, we can simply tweak things to suit our goals. Let me give you another example. This is R2-D2. Hopefully you all know who R2-D2 is. Okay, I have 2 legs and R2-D2 has 3 legs. If, of course, he's in a hurry. If he's not, he sucks up the 3rd leg and walks on 2. But let's say he's in a hurry. Let's look at these statements. R2-D2 has 150% more legs than me. I have 66% as many legs as R2-D2. I have 40% of the total legs. R2-D2 has 60% of the total legs. R2-D2 has 20 percentage points more than me. So what is more impressive? If you want to convey the fact that, you know what, me and R2-D2 are more or less similar, we could simply say that R2-D2 has 20 percentage points more. What is 20 percentage points? That's peanuts. If you want to convey that R2-D2 is way more, has way more legs than me, I can say the 150%, which sounds like a huge, massive number. If I want to prove that I have nothing compared to him, I can say that I only have 40%. Although the 40% and the 150% are conveying are talking about exactly the same thing, the message they're getting across is vastly different. So what we could do, in theory, we could cherry pick these and tell a story one way or another, which is scary. But if we understand math, if we understand how we see these things, then it won't scare us, because the reaction would be, yeah, so. Many years back, a friend of mine posted on Facebook a rant against a company that is making salt. This specific salt company is using something called potassium ferrocyanide in its salt. Potassium ferrocyanide has the ability to stop clumping in salt. So if you leave salt out in a humid place, you won't get clumps. And the rant was, why is this company using potassium ferrocyanide? Because potassium ferrocyanide is toxic. And the answer is, yes, it is toxic indeed. And the company goes so far by saying how much potassium ferrocyanide they actually put on the bottle. So people who don't have a good grasp of maths and how they actually work, and they don't have a good grasp of how this thought process works, they would say, you know what? This is a very bad salt, this is a toxic salt, I'm not going to get it. The truth is that if you see how much salt was included in there, how much potassium ferrocyanide was included in there, and knowing how toxic it is against rats, you can make an extrapolation and say, well, if that amount of potassium ferrocyanide causes problems in rats, this is how much it would cost per humans. Let's see how much we have in the packet of salt. So it's basically two divisions, nothing more. And if you were to run the maths, you would find that somebody would have to consume in one sitting 65,000 kilos of the salt in order to have any adverse effects. Now, granted, potassium ferrocyanide doesn't accumulate in your body. You literally pee it out. And I don't know what you think, but if somebody were to consume 65,000 kilos of salt in one sitting, potassium ferrocyanide might have probably been the least of their worries. And we came to that conclusion because we don't understand math, which is strange. Let me give you bonus points for my favorite misuse of statistics that comes from our lack of understanding of basic math. If you look at the data from DMV, is it called DMV? The Ministry of Transport and Motor Vehicles, you see that in the UK, on average, 30% of road accidents are caused by drunk people. Okay. By definition, that means that 70% of the accidents are caused by sober people. If you have 30% that are drunk, the 70% are sober. Which means it is safer to drink when you're drunk? Super strange if you think about it. Don't drink and drive, by the way. You have been very patient with me. You have been listening to me rambling on and on about this. We talked about Star Wars, we talked about Santa, we talked about this. And again, why am I doing this? Maths is a very interesting and very nice language. It is a language that helps us decipher the world. It is a language that helps us put a different perspective into things we are seeing. We can discuss all day long if something can happen. Yeah, I know the example of Santa Claus and Star Wars are extreme and non-logical and so on. But what if we used a similar logic to other things that makes us wonder? We shouldn't be afraid of maths. We should be embracing them and saying, oops, it's a tool we can use. It's a nice language. There is so much misinformation out there that can be avoided if we simply learn how to use maths. Let me give you a very current and up-to-date thing. Was it 3 weeks ago, I think, that the UK started vaccinating against COVID-19? And 2 days after that, 2 or 3 days after that, there were 2 health workers that showed allergic reactions. And there were big headlines everywhere about allergic reaction to vaccines, which prompted some people who unfortunately don't understand science, don't like vaccines, to say, ooh, vaccines bad because people got allergies. The correct approach to something like that would be, okay, let's see how many people got allergies against how many people that were vaccinated. And let's see now what the prevalence of allergies is in the general population. If I'm not seeing a difference between these two things, then why am I worrying? And the only way we can continue doing things like that is if we simply take over this thought process. Now, I'm not saying you should be doing this with everything, but I think it is about time we kind of stopped the what if this happened, what if that happened, and started thinking about how things can happen. I think it is a very interesting approach. Now, having said that, don't do this thing with everything. Don't go to the supermarket to get a pack of potatoes and start thinking with equations whether this pack of potatoes is better than the other pack of potatoes because one contains more potassium than the other one. It will drive you a bit crazy after a while. But still, I think it's a nice way that will help us realize how helpful maths can be. So, with that being said, I want to wish happy holidays to everyone. Don't go overboard with the digestives, but okay, perhaps Santa doesn't actually need them because I think Santa doesn't exist in the end. And that was it for me. Thanks a lot for spending your time with me. Hopefully your brain isn't ready to explode because of all these numbers and math and so on, but hopefully you kind of understand why I wanted to do this. This is one of the classes I gave at the university to my first years and my master students, parts of it, where we talk about things like mathematical analysis and so on. With that being said, thank you very much. And
thank you,
please,
George.
If you have questions or anything, fire away.
We've just got one in the chat at the moment. Do you still need your slides on? Or fantastic, thank you.
There you go.
Why does R2D2 have 150% more legs than you and not 50%?
Because R2D2 has 3 legs.
Uh-huh.
I have 2 legs. 3 is 150% bigger than 2. If my legs are the 100%, R2D2's legs are the 150%.
Really does depend how you put it over, doesn't it?
Exactly, and this is the point. Because unless we get a deeper understanding of these things, we can extremely easily be manipulated by people that play around with numbers like that. One of my favorite books of all time, it was written back in the 50s, and I highly advise it to everyone, is called How to Lie with Statistics. And it explains exactly this, how you can present facts, lie through your teeth, and have people say, yes, that is absolutely true. It is how we manipulate math. And as with every tool, if you know how to use them, you can understand when they're being misused.
And Georgia, have you ever thought to try and measure Christmas spirit?
No.
I'm a big elf fan.
I haven't. I've been doing the elf on the shelf thing with my daughters and they love it to death. They are being very naughty.